which is Wheatstone's bridge. In relation to that, we are going to see what is your Kirchhoff's law. So observe carefully. Congratulations to the winners of 14th as well as to the winners of 15th. So this is what I was telling you about. B.B. Roy of Great Britain had a very good wife. We had black, brown, red, orange, yellow, green, blue, violet, grey and white, and the colors which you can see. So 4 rings were there. The last ring was only for tolerance. Then you were able to see the first 2 rings. Directly we will write the numbers. The third ring into 10 to the power of. That is what we did. For those of you who missed the classes, we will do the recap when it comes to your thing. So these were done in your last class and we wind it up here. These are the winners for the last quiz. So today, to start with, we are going to learn about Kirchhoff's law. So you are very clear with Ohm's law. Ohm's law is the potential across any circuit will be directly proportional to the current and resistance, provided the temperature and other physical conditions should remain constant. That was your Ohm's law. Mathematically, we write it as V is equal to I into R. So V stands for voltage or potential difference. I stands for your current. R stands for your potential difference. Today, coming to your Kirchhoff's law, there are 2 laws which are given by Kirchhoff. First law and second law. First law has got 2 names. Observe carefully. It is called as the current law, or you can call it as the junction rule or the junction law. So before knowing what is this law, we learn a term which is called as junction. Now, trains are all not moving around. If they had to move, we call Bangarpet as a junction. Why we call it as a junction? Many trains come there and meet. Same way, here junction refers to a point where 2 or more current elements can meet. Current element means it can be your resistor or it can be your any element which carries current. So if 2 or 3 current elements are able to meet at a common point, then we call it as your junction. So if you can observe here, I is one current element, I4 is the second current element, you have I2, I3 and I5. Just see the colors. Red is away from the point O, arrow mark is outward. Green is towards the point O. So this common point O, where 5 current elements are meeting, we call that as your junction. So here junction is one point where 2 or more current elements have to meet. Now when they are meeting, there are 2 conditions. Either current can enter, as you see in the color green, or current can leave, as you see in the color red. So whatever is entering will be taken as positive, and the current which is leaving will be taken as negative. So what is the first law called is, or the statement of the first law is, the algebraic sum. That is, when you add all the current elements at a junction in any electrical network, it will be equal to 0. I am repeating it. The algebraic sum of the currents at any junction or at a junction in any electrical network should be 0. What is network is? It should be a combination of current elements. So I think it is clear. Current elements refers to the current terms which are there. So algebraic sum of the electric current at any junction in the electrical network should be equal to 0. Now how to make it to be equal to 0 is, this same law can be written in one more form. That is, at any junction, or you have one more term for it, we call it as a node, N-O-D-E. So at a junction or a node, the sum of currents entering the node should be equal to the sum of the currents leaving the node. So what is entering here? I1 and I2. When I use the term algebraic sum, it should be I1 and I4 will be taken as positive. Observe clearly. Green color arrow mark is entering towards O. So whichever is entering, I'm taking it as positive. Current elements leaving from the point O, we are taking it as negative. So observe, I1 is entering, so we take it to be positive. I2, it's in red color and arrow mark is outward. It's leaving the node, so it should be taken as negative. I3, again it is leaving the node, so you have to write it as minus I3. I4 is again entering the node, so you take it as plus I4. I5 is again leaving the node, so I'm taking it as minus I5. So my law is sum of algebraic currents at any junction should be equal to 0. So when it is equal to 0 here, you can clearly observe the sum of the currents entering is positive, sum of the currents leaving it will be taken as negative. So this is the first law. Algebraic sum of current at a junction in any electrical network should be equal to 0, and which is entering as positive, which is leaving will be taken as negative. You have sign conventions here. Incoming current will be taken as positive. Incoming means current which is entering inside, that is taken to be positive. Red color, what you see, current which is leaving. So from here, if it is going outside, that current you take it to be negative. Keep this in your mind clearly. If the current is entering, it is positive. If the current is leaving, then we take it to be negative. At a point, when you add everything, it should be equal to 0. That is the first law. To remember easily, you have something in your hand. Say you have 5 chocolates in your hand. If I add 5 more chocolates, it is increasing or decreasing? It will always increase. So that is positive. If I remove from your hand, it will become lesser. So automatically that will become negative. So this, when you solve problems also, it is important. Sign convention of current entering the node is positive, and sign convention of current leaving the node will be negative. So are you clear with this? First law, current law, or junction rule? Anybody has a doubt? Next to your participants thing, you have something which is called as raise hand. So you can raise your hand and tell me you have doubts. We will repeat it, or we will pause and continue with the video. So make it very clear. First law is current law, or we call it as junction rule. Algebraic sum of current at a junction in any electrical network will be 0. That's the first law. Coming to the second law, we call this as the voltage law. So what is this voltage law is? You have to use 2 terms, sum and product. Sum means what we are adding. Product means what we are multiplying. So there's a term called in any closed circuit. Closed means all connections should be done. It shouldn't be open. So in any closed circuit where current can flow, algebraic sum of product. So when I tell product, I should multiply. What are the 2 things we multiply? Current and resistance. So product of I and R. I is the current, R is the resistance. For example, I have 3 currents, I1, I2, I3. 3 resistances, R1, R2 and R3. How to put the statement into mathematical form? Product of current and resistance means I1 into R1 plus I2 into R2 plus I3 into R3. So you're going to multiply current and resistance and add them up. Then it will be equal to the sum of EMF. Question: what is the full form for EMF? As soon as the class finishes, send me out. We have already discussed it in the earlier class. What is the full form for EMF? That's the first question for today. So in any closed circuit, algebraic sum of the product of current and resistance should be equal to the sum of EMF. I told you 3 terms, I1, R1, R2, R3. Same way, EMF will be E1 plus E2 plus E3. Just look at this diagram, you'll be able to understand clearly. We have a cell here. Bigger line is positive, smaller line is negative. EMF of the cell is denoted by E1. I have one resistor here that is denoted by R1. Second thing, E2, and the current here resistance will be denoted by the symbol R2. You have one more in between, R3 resistance. R2 is connected across the diagonal, and you can see there are no cells here. Only EMF will be present if cell is connected. We are taking this just for an example. So one cell is there connected to R1, second cell is connected to R3, resistor R2 has no connections in between, and it is connected across 4 terminals, that is A, B, C and D. Always current will flow from positive terminal towards the other side. So you can see the direction of my arrow mark. It is starting from E1 towards A. Since this is the first cell, current here will be I1. Now if current is flowing here, what should be the symbol? That should be equal to I2. So from positive, it has to move, and this can move up towards the upper circuit. Keep it clear. E1 current flowing is I1. E2 current flowing will be equal to I2. And always current will start only from positive. In the cell, bigger line is positive, smaller line is negative. The two cells we have, I'm indicating two currents, I1 and I2. Now when it comes to this point, first law we saw, this is called as a node, or you call it as a junction. I1 is also coming there, I2 is also coming. So what will flow towards C? It will be the sum of I1 and I2. You can see clearly. I1 is also meeting here, I2 is also meeting at this point. So when it flows, it will be I1 plus I2. The next thing is, this current I2 can make a circle like this, and it can move across R3 also. It's starting like this, so it will go to A, then to B, then to C and reverse back. Same way, your direction of I1 is also indicated. Now in this second law, you can give the direction. We can assume whether current is flowing in clockwise direction or anti-clockwise. Don't get confused. You know, in your clock, after 12 you have 1, 2, 3, 4. So if it's moving in that direction, we call it as clockwise direction. If it is moving in the reverse direction, opposite, 12, 11, 10, 9, like that, if it is going to move, then we call it as anti-clockwise direction. I am assuming it to move in along your clockwise direction. So what to do here is, if direction of your current and the direction of the circuit both are same, then it will be positive. If it is different, it will be taken as negative. Now see this, observe carefully. I am taking a loop. Loop is one part of the network. See, this is like a rectangle, but in between I have a line. So I can divide this into two triangles. One is ABCA. The second one can be ABC and A. See, this rectangle is divided into two parts. One triangle is A, B, C and A. The second triangle is A, B, C and A. I'm taking the first part, that is A, B, C and A. This upper portion of the triangle. What is our law? The algebraic sum of product of current and resistance will be equal to the EMF. Now what is the current flowing here? It is I1 and R1. So I'm taking the direction like this. I1 will flow across R1 plus across R2. What is your current? It is I1 plus I2. So I1 plus I2 into R2 should be equal to, what is the EMF here means? It will be E1. I'm repeating it. We have two resistors, R1 and R2. Current flowing through R1 is I1. So multiply both. I1 into R1. Second resistor is R2. Current flowing across that resistor will be I1 plus I2. So I1 plus I2 into R2. If you add both, it should be equal to the EMF, which is E1. Just for comparison, see this loop now. So it will be I2 multiplied by R3 plus What are the resistor we have? I1 plus I2 into R2 should be equal to, the EMF here is going to be E2. So whichever cell is there, you can write it like this. I2 into R3 plus I1 plus I2 into R2 should be equal to your EMF, which is E2. This is your law. I'll put it in a nutshell. Product of current and resistance should be equal to the EMF. That is the second law. Conditions are there. Circuit should be closed. In any closed circuit, algebraic sum of product of current and resistance should be equal to the sum of the EMF. So these are the two laws to learn. First law is, at any node or junction, the algebraic sum of the current should be equal to 0. Whichever is entering, we'll take it as positive. Current which is leaving, we will take it as negative. Second law is also called as your voltage law. In any closed circuit, the algebraic sum of product of current and resistance will be equal to the sum of your EMF. Check your sign convention. EMF will be taken negative when we transfers from positive to negative. If it's from plus to minus, EMF will be taken as negative. EMF will be taken positive when we move from negative to positive. This will be when you solve problems. Just keep this in mind. Now, having studied your first law and the second law, I already told you the path can be in clockwise direction or in anti-clockwise. That is depending on us. We assume this is in clockwise. If I want to give it an anti-clockwise, I can reverse it. For this diagram, they have used clockwise direction, and this is what is the condition which is given to you. So in statement form, Kirchhoff's laws or rules, very important 2-mark question. Junction rule: in any electrical network, algebraic sum of the current at any junction should be equal to 0. Sigma, the symbol means summation. So this law has a significance. Why we should use this law? It is used in law of conservation of charge. Keep this in your mind. First law, application or significance is law of conservation of charge. 1-mark question. What is the significance of Kirchhoff's first law? You should just write, it is to satisfy the condition of law of conservation of charge. Second law, in any closed loop, algebraic sum of EMF will be equal to the algebraic sum of product of current and resistance in that mesh. So I will just put the slide to show you that loop and mesh both are same. You can interchange. First write product of current and then write EMF, or write EMF first and then interchange it. So sigma here is E denotes EMF, I denotes current, R denotes your resistance. Significance of Kirchhoff's second law is law of conservation of energy. First law, charge. Second law, law of conservation of energy. So my first question for you, what is EMF? Second question, I want you to answer, what is the significance of first law and what is the significance of second law? Just now I told you what law it satisfies. So first question is, what is EMF? Second question is, what is the significance of first law and what is the significance of your second law? Now what we are going to derive is a 5-mark question. Keeping your Kirchhoff's law, you should derive Wheatstone's bridge network. What is this wheat and stone? Don't get worried. It is the name of a scientist who found it out. So Wheatstone is the person who derived this. I want you to observe clearly. These are 4 resistors: P, Q, R and S. How to draw this means, draw one diamond shaped structure, in between put 4 resistors. Start P on top towards your left hand top. P, 1 resistor, Q, then you have R, then you have S. These end points what we have, name it as A, B, C and D. You can do it in your book simultaneously. You will be able to follow it up faster. Just draw one structure of a diamond shape, put resistors in between, ends label it as A, B, C and D. Resistors P, Q. Below P you should write R. Below Q, you should write S. I will share the slides to you after the class so you can see with the notes. Now, clearly, these diagrams should indicate the arrow mark. If arrow mark is not written, full derivation is done also, they will not give you marks. So, make a count to put the arrow marks correctly. Follow up. We are drawing 4 resistors, P, Q, R, S. Terminals are denoted by A, B, C, and D. Now, across the terminal A and C, I will connect one battery or a cell and a plug key. Plug key is a safety instrument. I can close it so that the circuit will not get shortened. So plus is the bigger line, minus is the smaller line. I told you current will flow from positive side. So the total current is taken from the positive, arrow mark denoted with the symbol I. For this whole circuit, the current should go like this and return back. That is the direction of I. Here, the current is splitting into 2. So when it goes to P, the current is I1. Okay. When it goes to R, the current is going to be I2. So be careful with the arrow marks. It has to start from positive. Here it's splitting into 2. On top, I will write it as I1. Down, I will write it as I2. Now the same current will flow up to B. Now at the point B, the current is splitting into 2. Center, I have written G here. This is nothing but your galvanometer. So what is Wheatstone's bridges? It consists of 4 resistors PQRS connected in the form of a quadrilateral. Quadrilateral is a 4-sided figure. For the 4-sided figure, across 2 ends, A and C, a battery will be connected. Across the other 2 ends, B and D, a galvanometer will be connected. Galvanometer is a device used to measure current, or it is used to detect the presence of current. If current is there, the needle in the galvanometer will show reading. If current is not there, it will not show any deflection. So keep it clear. 4 resistors in the form of a quadrilateral. 2 ends, one cell will be connected. Across the other 2 ends, a galvanometer will be connected. Okay. Now we saw the current I is splitting into I1 and I2. Here what current is going, I have to denote it with the symbol IG, capital I and small g. You can see it here. This is the current through the galvanometer. This is first part. Now from here, when it is moving, total current which is coming to this point is V. I told you at any point, current entering is positive, current leaving is negative. See, at the point B, current entering is I1. But what is leaving? IG. That's why we have written I1 is positive, IG is negative. So here it is I1 minus of IG. Same way, look at the terminal D. What is entering here? I2. IG also is coming towards G. So that is also taken as positive. So at the point D, your current is I2 plus IG. Only this diagram is asked for 2 marks. If they ask you to derive it, it is a 5-mark question. So what we are labeling here is total current is I, this side I1, down it will go as I2, to G your current is IG. Q where you have it is I1 minus IG, and S where you have it is I2 plus IG. Now when you describe your diagram, you have to make a mention of what is Wheatstone's bridge. 4 resistors connected in the form of a quadrilateral. Across A and C, a cell or a battery is connected. Across B and D, a galvanometer is connected. I is the current throughout the circuit. Current through P is I1. Through R, it is I2. Through G, it is IG. Q, your current is I1 minus IG. S, your current is I2 plus IG. So you have to mention that PK here is plug key, BK here will be your battery. To start with your derivation, observe carefully. Current flowing through different branches of the bridge will be shown as shown in the figure. So your diagram we've already shown to you. Applying KCL, that is Kirchhoff's current rule. Current rule in the sense it has to be your first law at the junction A. So at this point, what is your Kirchhoff's first rule? What is our rule? Current entering the node should be equal to the current leaving the node. So I will take total current I is equal to I1 plus I2. Call that as equation 1. We are taking the derivation to be along your clockwise direction. So you can see I is like this, I1 and I2 are moving in the reverse direction. So I will be equal to, which is entering here, the current I is entering. So that should be equal to what current is leaving? I1 and I2. So at the node A, capital I is equal to I1 plus I2. Call that as equation 1. Now when you apply Kirchhoff's voltage rule to the mesh A, B, D and A, we'll see how much you are following it. Second law is product of current and resistance. Now here P is the resistance. What is the resistance across P? Current is denoted by I1. So I can write I1 into P. I'm not writing any sign. Here it is IG into G. Third term is I2 into R. I'm repeating it, only half triangle we are taking. First one is I1 into P. Second one is IG into G. Third one is I2 into R. We don't have any cell here. So EMF will be equal to 0. Now you can see here I1 is moving forward. So that will be positive. IG is moving forward. That will be negative. See I2. If you take the direction, it should go up from B to D. Then it should have come from D to A. But the direction is opposite. So only that term will be taken negative. I1 into P plus IG into G minus I2, because it is not in the direction of the flow. That will be equal to 0. Equation 1, Kirchhoff's first law, voltage law I am applying for this loop. Now when you apply Kirchhoff's voltage law to the second side of your mesh, that is towards this side, very clearly, Q into I1 minus IG, S into I2 plus IG, IG into G should be equal to 0. Check your direction. This is positive, this is negative, and IG again is negative. So I1 minus IG into Q minus I2 plus IG into S minus IG into G should be equal to 0. I can multiply this inside. I1 into Q minus IG into Q minus I2 into S plus IG into S minus IG into G will be equal to 0. Multiply Q with these two terms, multiply S with these two terms. Very important condition for balancing. Current through the galvanometer should be equal to 0. So what does 0 means? IG should be equal to 0. So when IG is 0, I want you to substitute in equation 2 and 3. In equation 2, where you have IG term, that will become 0. So what will I get? I1 into P minus I2 into R should be equal to 0. Apply here. First term, there is no IG. So you can write that down. I1 into Q. This term will become 0 because IG is there. Then you will have minus I2 into S. Again, IG is there. So this will become 0. This will become 0. You will get I1 into Q minus I2 into S should be equal to 0. We are applying condition to equation 2 and equation 3. Wherever IG term is there, that term will become 0. So first I will get I1 into P will be I1 into P minus I2 into R will be equal to 0 you will get. So if you take it to the other side, it will become positive. Same way here. I1Q minus I2S is 0. Take it towards the other side. I1Q will be equal to I2 into S. You have to divide equation 4 and 5. So I1P divided by I1Q should be equal to I2R divided by I2S. You can cancel I1 and I1. I2 and I2 can cancel. We will get P by Q is equal to R by S. This is our balancing condition for your network, or see resistance in the upper arm will be equal to the resistance in the lower arm. P by Q should be equal to R by S. That is the condition for your Wheatstone's network. And this is a 5-mark question. A quick brief up. At the node A, I will be equal to I1 plus I2, equation 1. Applying voltage law to the loop A, B, D and A. I1 into P plus Ig into G minus I2 into R will be equal to 0. Third point, applying KVL to the second part of the loop B, C, D and B. Q into I1 minus Ig minus S into I2 plus Ig minus G into G will be equal to 0. Then multiply I1 into G minus Ig into G minus I2 into S minus I2 Ig into S minus Ig into G should be equal to 0. Fourth important point, for balancing condition, Ig should be equal to 0. When your Ig is equal to 0, equation 2 becomes I1P minus I2R will be equal to 0. Equation 3 becomes I1Q minus I2S will be equal to 0. Divide equation 4 and 5. You will get I1 by P divided by I1Q should be equal to I2 into R divided by I2 into S. Cancel out the like terms. I1 will get cancelled. I2 will get cancelled. We will get P by Q should be equal to R divided by S. So when you write that, that is called as the balancing condition for Wheatstone's network. So for today's third question is, what is your balancing condition for Wheatstone's bridge? So with this, we stop for the class for today. You have any doubts, you can clarify. Yes, any doubts, you can get it clarified. First question is, what is EMF? Second question is, I want you to write what is the significance of first law and second law. Third question is, what is the balancing condition for Wheatstone's bridge? All three answers together, I want you to send. You have already sent it, but I